Welcome to the Maine Science Podcast. I'm Kate Dickerson. Today's episode is a conversation I had with Asheesh Lanba, an assistant professor of mechanical engineering and director of research at the Composites Engineering Research Laboratory at the University of Southern Maine. Asheesh is a deeply passionate researcher, mentor, and educator, and all of that comes through in our conversation, which was recorded in June 2025. Asheesh was one of the 5-Minute Genius speakers at this past year's Maine Science Festival, and I've included a link to his talk in the show notes. I hope you enjoyed this conversation as much as I did. Asheesh, welcome to the Maine Science Podcast. I've been a fan of yours for a shorter amount of time than many people I speak to, but I heard you speak at a regular meeting a couple of months ago about a startup company you had, and I thought, this guy is so excited about his work. I got to talk to him. And then we were lucky enough to have you at the Maine Science Festival. And it's hard for me to adequately or concisely describe what you do because there's so much. So before we get into all of that, I was hoping you could let me know, what is it that got you into science and engineering? Was there a spark at any one point?
Yeah. So thanks for having me on, Kate. And yeah, just to go back to what you said earlier, thanks again for having me on for the Maine Genius series. That was an amazing experience. And I felt like I was in very privileged company. What got me into science and engineering? My dad was in the Navy and my mom was a school teacher. She still is. And they wanted me to excel in life. And there was a sort of sense that they wanted me to do better and achieve my full potential, which I think my dad always had regrets about working in the Navy for a really long time. And my mom always felt she could have gone and done further studies. So they always wanted me to reach my maximum potential, be it in whatever activity I was doing, right? In schooling, in sports, and things like that. And as it turned out, I was a big nerd always growing up. Some of the things that you find in my background common with the children in America. I was born and raised in India, by the way. And yeah, it was like, I was crazy about dinosaurs. I was crazy about space, I was crazy obsessed with NASA growing up as well. And then I just, all throughout my life, started showing a lot of interest in math, physics, and to a lesser extent in biology and chemistry and programming and computer science as well. And when I reached close to high school age, it was really like math and physics were I was really good at, and I really enjoyed problem solving, essentially. Like when a problem was given to me, I really, really enjoyed going through all the steps and matching answers, going to the back of the book and seeing that I had matching answers. And that's what I ended up focusing on. So within physics, I was really interested in mechanics, which is basically the physical science of forces, the cause of forces, how they cause motion, and things like that. So my top choice in undergrad was to try to do aerospace engineering, but I didn't get into that program. My second choice was mechanical engineering. I went to undergrad in Singapore to the Nanyang Technological University, and it was great. I learned so much there. I did a bunch of undergraduate research projects as well. And I also worked at Singapore has one of the largest oil refineries in the world. And so I worked for 6 months, like we had an engineering internship program. And I really liked what they were doing and I liked the engineering behind it. But I was a very idealistic 20-year-old and I decided I didn't want to work for a big oil company. So I didn't know exactly what I wanted to do professionally. So I said, why don't we just go to school for longer? Which pros and cons with that decision as well. But yeah, that's what led me to come to the US. And I've been here since 2009, did my PhD at Penn State University for 10 years, where my degree was in engineering, science, and mechanics with a focus in material science. And then I worked at a startup for 4 years at Penn State in one of the incubators there, with the laser imaging technology that I spoke about, LATSCAN, laser ablation tomography. It remains one of my research foci. And then I've been in Maine since August of 2009. As an assistant professor of mechanical engineering, I was hired specifically for my expertise in material science. And I've been extremely lucky and very, very privileged to have access to all of the tools that I do at the University of Southern Maine. There was basically a material science lab that was just handed to me, which is the Composites Engineering Research Lab. Like it's fully furnished to study the material science of composites, particularly from this aspect of polymers and plastics. Before coming to Maine, I did not have an expertise in polymers and plastics, which I've developed and, commercialized with Stoke Plastics over the last couple of years. But, we spoke about this a little bit, and I don't think of myself as a scientist. I tell my students that I'm very lucky because I get to be a child at work and play around and do experiments and play with things and make things. So thankful for that every day.
So it's really interesting because mechanical engineering, my understanding of it is it's a lot of people that I know when I went to undergrad who were mechanical engineers, they were like car guys first. Like it's very engine focused. And I know that's not the only thing about mechanical, but that's like my pervading memory of it. And materials is really different. So what was your ramp up to figure out how to attack that? And just to give people a sense of it, like if you want to talk a little bit about some of the different materials and work that you're doing, I can see parts of mechanical in it when you've talked about it. It's really cool, but it is a deep dive into very different kind of engineering.
Sure. Yeah. And you're absolutely right. When people do think about mechanical engineering, they do think about, cars and planes and things like that. And that is a big part of it. But I tell my students this all the time. Mechanical engineering, and this is okay, right? Mechanical engineering is a wide array of engineering. And therefore, basically, it's like an engineering degree for engineers who don't know what they want to do. And they can learn that as they're getting their mechanical engineering degree. 40,000 foot view, mechanical engineering is a degree in problem solving where you can attack a problem by taking it apart and putting it back together, or by putting something together and making sure that it works. That can be a car engine. That can be the outside components, the composite components that go on an airplane. Or that can be a problem in acquiring data from like material science and doing it as a data science problem, like a machine learning problem as well, or an artificial intelligence problem too. So it really gives you a wide base of knowledge that you can apply and then focus in on, or not as well, right? Many engineers get a mechanical engineering degree, work as a process engineer for a couple of years, get an MBA degree, and then become like an engineering manager where you're managing a bunch of different things. And that is also a totally acceptable way to look at it as well. But what I do right now, what we've got going on in the University of Southern Maine, I've got 3 basically research arms where one of them, and these are also very widely applicable, and I'll give you some specific examples as well. One of my arms is working with advanced materials where we're looking at new material behavior, and we're also looking at how to make practical applications out of that material behavior. The second research arm is for my laser imaging technology, laser ablation tomography, or LAT scan, which is basically a 3D microscopy technique where we use it to image things. And the third arm is more of that first arm where we're developing engineering applications like medical devices and things like that. So one example of the advanced materials is with the Stoke plastics, as I've spoken about before, where we are basically making plastic pellets out of plastic bottle waste that is ocean bound and ocean found, with the goal of removing that plastic pollution from the ocean, because we need to shut off our fossil fuel dependence, especially with single-use plastic, so that we curb the problem of plastic pollution. Another materials science project that I work on is with these alloys called shape memory alloys. They're basically what I got my PhD degree in. They are these alloys that respond to external stimuli like temperature and stress. So you can bend them, heat them up, and they'll remember their original shape, or they're like springier springs. So if you stretch them out like a spring, they'll remember their original shape back. Much more so than like what steel or aluminum might do with the regular springs that we see. So I'm right now working on a very exciting project in collaboration with the University of Michigan, which is funded through the NSF, where we are using this material and combining it with rubbery elastomeric material, which is like silicone. And we're trying to see if we can transfer that high deformation from nitinol onto the elastomers, because then we can use these composite test beds in a myriad of applications like controlled drug delivery, soft robotics, stretchable electronics, because this can act as a base for all of those things with the large shape recovery and this soft base on it. So that's talking some of the stuff with advanced materials. With laser ablation tomography, basically it's a 3D microscopy technique where we use a high-powered laser to serially section material and image those sections, and then we stick those sections together to make 3D models. What's amazing is that due to the ultraviolet nature of the laser, we get fluorescence in those sections, which right now we collect as RGB data, but I'm trying to get funding to actually map out the chemistry in 3D as well, because there's no other technology that maps chemistry in 3 dimensions. At that scale, you have to go a scale down into electron microscopy when you map 3D chemistry. And then with developing medical devices, again, this was my privilege as well, working at USM. There's this amazing doctors at Maine Health that have these ideas. And they're like, can you help us with the next phase of the prototyping? So one of them was this gastrocutaneous wound closure device, which is for this pediatric surgeon who basically saw that when they put gastrostomy tubes into kids and they remove them, they have to come in twice. Basically, once when the wound closure clip is put and another time when the clip has to be removed. So he said, why don't we close the wound from the inside? That will not require anesthesia and they only need to come once, because then once the wound closes, the clip can just pass through the GI tract. He's an amazing, super smart doctor, Dr. Jeff Halter, who bought a 3D printer, made this concept, and we helped him use some real world materials and make the next version of the device. So that's an example of one of the medical device applications that I've had the privilege of working on. Yeah, that answered all of the stuff that you asked. I feel like I'm forgetting something.
Well, I think you're probably only forgetting something because you have so many things going. I want to go back quickly. You said you were part of a startup for 4 years.
Yes.
Which is its own interesting, kind of fascinating bit. I'm curious, why go from a startup into kind of academic work?
That's a great question. So during my pursuit of my graduate degree at Penn State, the question I would keep finding myself asking was, what about this experience I'm having is enjoyable that I want to do as a profession going forward? And the thing that I enjoyed the most was teaching when I was in grad school. So I had the privilege of being a teaching assistant for a bunch of different classes for undergraduate and even for graduate students, where I had to give lectures, act as a tutor. And it was very enjoyable. I enjoyed seeing the spark in the students' eyes when we were problem solving and they were getting it. And it was just a fun experience, which I knew I wanted to do at some point in my life, if not immediately right after grad school. Grad school itself, my research experience was a little bit jaded because, I was my advisor's first student and our working styles never quite matched up. And I'm sure you've heard this from a lot of people who go to grad school about issues faced in grad school. So there was this big power dynamic and stuff like that. And I was lucky that I had a project good enough where I was able to get a bunch of research papers out and things like that. But I just ended on a very jaded note. The last couple of years, I was like, I'm just going to do whatever's the minimum amount that I need to do to get the degree done with. And that wasn't a very good place for me personally. Ideally, with my background, I would have gone on to do a postdoctorate at one of the premier research institutes. But I was just so jaded that I just finished my degree, I defended my thesis, and I just took 4 months off and I traveled the US, which was amazing. I drove 15,000 miles and just saw how beautiful America is and what an amazing culture of conservation we have over here in terms of the outdoors. And I love the outdoors. One of the reasons I moved to Maine as well. And then when I was reaching the end of that road trip, I was like, I guess I got to figure out what I need to do in life now. And I didn't have a clear direction as to what I wanted to do. I just haphazardly started applying for jobs. But then my friend who invented this laser ablation tomography, he's a very good, one of my closest friends. He's the one who invented the technology at Penn State, and he had started the company commercializing it. And he told me they were getting this big project, and he was telling me, can you come help with this project and stuff? And I'm like, sure, I'll just come. And the deal I made with him was, I'll come help you out. Don't even pay me for my time, whatever, but he did end up paying me. And I'll just continue my job search. Another important aspect for that is that being a foreign national, I need a job to have a legal status in the country as well. So that was part of it too. So I ended up going there and I really enjoyed the work that they were doing. It was completely left field from my graduate education, nothing to do with material science. It was more of engineering problem solving. How can we take these 2,000 stems that we're getting from this big company and image them in a timely manner? So I was basically involved in the automation side of things, essentially. So we had this repeating project that we got every year. And I was able to, thanks to my quote unquote programming skills, I would never call myself a programmer, but it ended up doing that. I did a lot of programming there. But yeah, we were able to cut down the processing time from 2 months to a week because of automation that I was able to enable with all of that imaging that had to happen. So that was my big claim to fame. But I was also very lucky to have that experience because I learned a lot about the startup world. Biggest lesson being that, when you're a part of a small team in a startup, you can't do the one thing that you were hired for. You are going to end up having to do many different things. So I got involved on the marketing side of things. I got involved in the outreach side of things. I ended up being the guy that designed the t-shirts that we were wearing when we went out to conferences and stuff like that. So I ended up learning a lot. And also the important skill was learning a lot about how companies work and, setting up a company and how that stuff goes in the US, which has served me well in Maine as well, especially with the new startup that I'm a part of with Stoke Plastics. And yeah, it was a wonderful experience. Now, hindsight is always going to be 2020. So would I have done things differently? Yes, absolutely. I would have. But here we are, and I don't have any complaints, as to speak. So
it's kind of its own interesting postdoc, really.
It is. And that's what it ended up being, because the way that the technology works is that it's new. Not many people have used it and they see a lot of potential in it, but then not many people have the funding to pay for it. So I run essentially now the research arm of it with these researchers. I do the collaboration. We have a system at USM and we use it as a research tool for them, right? So when they need to do imaging, they come to us. And if they can't pay for it, then they come to me and then we do it as a collaborative research project. I worked there for 4 years and I ended up getting 3 or 4 publications, which would, not the best postdoc, but not the worst postdoc either, like an average sort of postdoc. That's what I was able to sell it as when I got the job at USM. But the real good thing about USM is that when I was hired there, they were able to see the potential, not only from the research perspective, but also from the entrepreneurial perspective as well, the experience that I brought with me. And that's what they are helping me foster right now, and very, very helpful to me.
I'm curious, how many undergraduate students are you able to bring onto these projects? That's another form of teaching that I often talk about with people, but I haven't really leaned into the really important parts of teaching undergrads how to do research.
Yeah. So right now I have in the Composites Engineering Research Lab, I've got 3 students. In the engineering department, I've been working with one student who is now graduated, but he's continuing on in the engineering department as our lab manager as he's pursuing his MBA degree at USM. I have another student as well who's working on a different project. So I have 5 students. But like last semester, I was on parental leave. And this following semester, I'm on a sabbatical. So I'm technically on leave, which my wife reminds me of. But the wheels of research must go on turning. So I have 5 students that I work with right now, 2 of whom are shared with other faculty members in the engineering department. They split their time. But usually I tend to have between 5 to 10 students over the space of a year. And that's not just with the research that I'm doing, but I also tend to get a lot of students who are in their senior year and working on their capstone design projects as well. And the way we work with the capstone design projects is if the students have an idea, I never want to take away their ideas from them. So I help them develop their ideas and work with that. And if they don't have ideas, I always have projects for students to work on. I've got like a giant set of notes on my phone about projects that students can do. So one of the students I'm working with, she's going to be going to Michigan with me actually in a week's time. And that project is for 2 years over the next 2 summers. And yeah, we're doing a bunch of different things. None of what I do would be possible without the students, because I always told myself in grad school that I'm never going to be the kind of advisor that's never in the lab. I'm always going to be with the students in the lab and working there. And I still try to do that as much as I can. But I joke with my friends and colleagues and I tell them academia, 90% of the job is filling out forms, right? So that's what I do. Sort of form filling, a lot of filling out applications and a lot of grant writing and things like that too, which is fun in its own way. But no, I'd much rather just be playing around in the lab.
Yeah, I think that's one of the hardest things for a lot of people who go into academics is that they don't get to do the deep thinking work that got them in that job in the first place. You have to maintain the research and you have to run the shop to pay the bills, which is actually a really good segue. You've mentioned a few things I want to hit on because I think they're really important. And one is NSF funding and other science funding, which is anybody who's been listening to this podcast for a long time knows how valuable and important science research funding is. And you also talked about being not yet a citizen. Are you a citizen yet or not?
No, not yet. I'm a permanent resident right now.
Permanent resident, which sadly has been in the news a lot from the perspective of somehow thinking that this is not valuable. So first of all, I want to personally thank you for coming to the US. And actually, I think you have probably seen more of the United States than many of us have. I've only ever driven and seen like the top part of the States, and I've seen a little bit of the Southwest, and that's it. And there's a whole lot of the country I haven't seen.
The Southwest and the Northwest are amazing. And California.
Yeah, I mean, they're so different, right? We have so many different cultures in this country. But I would like to give you the opportunity to talk about the value and the importance of science research funding. And then what, from your perspective, if you don't mind me putting you on the spot, what is the value that we have for having really diverse people represented and doing research? Because I think, the more people you have with different perspectives, the better. But I'm not actually doing the research. So I think maybe hearing from someone who does is better.
In engineering, one of the ways to solve problems is to attack it from many different perspectives. On a fundamental level, when you have people working and you have people doing science, the more diverse perspectives you have, from more diverse backgrounds that you have, the more higher probability of success you have going forward. What is currently happening in this country is insane to me, because America has built a system since the 50s, since post-World War II, that has successfully attracted the most talented people in the world in what they do to build the world's richest country in the history of the world and the most thriving middle class in the history of the world, which, from my opinion, is what you need to have a happy, healthy society. Is it perfect? No. There are things that can be done to make it better, to make it easier to solve problems. But can it be done better? For sure. But they've taken that aspect of, hey, can we do science funding better? And from the solutions that need to be implemented, they're just going in the complete opposite directions. People don't want to come to America anymore, from what I speak to my friends who live abroad, and they don't want to run the risk of getting arrested at the border and things like that. I know people who are in my circles who are actively meant to go on the job market this year and become research scientists, who are now applying for jobs abroad in Europe, in Australia, in Singapore, Southeast Asia, all these places. Every research dollar that is spent, the amount that's generated in startups and these ideas that have come about is like close to $3 or $4. I might be misremembering that, but I think that's where the number is. Yes, can that number be higher? Can it be $5 or $6? Absolutely. But you're not going to get that by stopping ongoing research projects, by attacking science that you think is dubious, by stopping all research funding for social science and things like that, for non-STEM related work. What we're going to have is, when you cut research funding like this, I'll give you an example. We started a collaboration with a lab at Harvard where they do research with these animals called axolotls, amazing animals. Their genome has been mapped and they can regrow their limbs. And, for a bunch of clinical research that will apply to humans for medical research. You cut their research funding, you're not going to have people who manage the animals anymore. There's going to be bad consequences of this stuff that ends up happening. I don't know. It's absolutely crazy. And again, can science be done better? Absolutely. We can all be always improving, always learning, always streamlining, always making things better. So with that in mind, let's get together and do that. But you're not going to achieve that by just completely turning everything off, gutting the system. Sorry, I tend to get emotional about that.
I've had a lot of conversations with a lot of researchers, both on our podcast and otherwise, and I know it's really raw. And I think one of the most important things to remember is what you said when you first started, which is you need a diversity of viewpoints to see problems in a new way to solve them, right? The funding it's not its own issue. It's a key part of it, but there's a deep need in science, I would say, in culture and everything. The more perspectives you have, the broader you are, the less likely you are to fall into kind of the same way you always do everything. And that way you get innovation.
The broader the view, the more perspectives you have, the more likely you are to solve the problem, the more likely you are to overcome challenges that come in your research. And the more likely you are to, even if you can't overcome them, reframe the challenges and present those in a beneficial way.
Again, I know this is not just a theoretical conversation for you. This hits very close to home, and I appreciate it. And I just think it's a really good reminder for all of us who have a deep love and care about science, culture, engineering, all of those things, we need to not, cut off our nose to spite our face.
Exactly. That's the saying in English. There's a saying in Hindi where I'm from that don't take a shovel and shovel your own foot into the ground and cut it across as well. So, yeah.
That is good and graphic as well. Do you have a favorite research project? Doesn't have to be a current one, but just circling back to this, because you're doing so many different things, do you have a favorite? And it can be a favorite for any reason. It can be a favorite because the problem you're solving. It can be a favorite because of the obstacles you've overcome. It can be a favorite just because it's the most fun to do. I'm just curious.
I wouldn't say I have a favorite. I more so say, and again, I find myself becoming the advisor, the principal investigator I say I wouldn't become, right? Like, I know, for example, the lab where my wife works, he's like one of the most prominent researchers in his field at Yale University. And he's got like lab of 25 postdocs, grad students. And most people are always saying that, yeah, he's amazing, he's great, but I wish I could get some more time with him and stuff like that. So I don't want to say that I have favorites, but right now, because we're leaving in a week's time to go to Michigan, all guns blazing on our collaborative project with University of Michigan, where we are basically trying to make these active composite test beds, which again, with these shape memory alloy materials, we are exploring these shapes in these materials called auxetics, which are basically geometries. So typically when you pull a material and stretch it, it's going to compress in the transverse direction, right? That's because it's of conservation of volume. But with an auxetic shape, what happens is that when you stretch it in one direction, it expands in the transverse direction. So it basically becomes this two-dimensional expanding shape, and it's purely a function of geometry. The shape memory material alloy that I work with is very difficult to machine and make complex shapes out of because it's a very hard material to cut. So we are using our laser processing, of course, because lasers solve all problems, to cut these complex shapes out in the nitinol. And then we're using that as like a functional skeleton, so to speak, surrounded and within silicone. And then the goal is to have those expanding properties translate onto the silicone, and then we can use that for many different applications because you have this expanding soft elastomeric base. One of the ideas we're going to explore is when you stretch this out like a Band-Aid, you can put drugs in it, and then it has like a little bit of drug delivery that which decreases as the wound is healing. That's one idea we're going to approach. And again, when you stretch it and you heat it, it recovers its shape back. We're going to see if we can do something with making like modules for soft robotics with that potentially. But yeah, you open up a myriad of different application potentials if we can figure out how to transfer the deformation from the alloy, the shape memory alloy, onto the soft elastomer.
That is mind-boggling to me, the idea of the applications being across from robotics all the way to drug delivery, number one. Number two, I wasn't fair when I said pick your favorite. I knew that when I said it, so it's really not a fair question. It's like asking who your favorite child is. So I appreciate you playing along with that.
I have two dogs, and I certainly have a favorite dog. So
I'm going to let that one sit right there. I am not going to touch that one. Asheesh, I could talk to you for many more hours, but I didn't even realize you were on parental leave. So now I feel like I'm stealing time away.
No. I've been completely, I'm lucky my mom is here as well from India, helping out a lot. So,
oh, that's great.
Very lucky, very privileged. Yeah.
But this has been a really great conversation. I hope I did not get you worked up too much for the rest of the week by poking the bear. I want you to know I appreciate so deeply your enthusiasm for science and teaching and engineering. I think it's actually inspiring. I think if I had met you when I was younger, I would have been able to understand first what engineering was, and secondly, possibly would have gone into it because you are so passionate about it. It comes through in every conversation I've had with you. And it's just really fun to be part of these conversations. So I really appreciate it. And I appreciate your work.
It's funny you say that. It's just who I am. And I take that as a huge compliment. So thank you so much.
Thanks for listening to the Maine Science Podcast. Make sure you never miss an episode by following us on your podcast platform of choice. And please leave a rating and review. It will help more people find us and help spread the word about some of the remarkable people doing science in Maine. The Maine Science Podcast is recorded at Discovery Studios at the Maine Discovery Museum in Bangor, Maine. Maine Science Podcast is executive produced and hosted by me, Kate Dickerson, and edited and produced by Scott Loiselle. And the Discover Maine theme was composed and performed by Nick Parker.